today we're going to be tackling machine learning.
Machine learning.
Or as the cool kids call it.
That's right.
ML.
ML.
And you've provided some really great material to work with.
Yeah.
Excerpts from a hands-on ML book covering everything from data visualization to neural networks.
It's going to be a fascinating journey.
It is. This book is packed with practical examples and techniques.
For sure.
And I'm excited to kind of unpack some real gems that'll make our listeners
absolutely
sound like ML whizzes by the end of this.
I think so. Let's see if we can pull it off.
Okay, so why don't we start with something that the book really emphasizes?
Okay.
Which is the power of visualizing data.
Yeah.
Especially for understanding things like housing price trends.
Yeah, visualizations are incredibly powerful tools. I think people really underestimate them.
Yeah.
They can help us see patterns and relationships that might be hidden.
Oh, for sure.
Raw data.
Yeah. And the book uses a great example with California housing data. They plot longitude and latitude on a scatter plot, and guess what?
You can see where people live.
You can see clusters of high population density,
right,
which of course are linked to housing prices.
It's a simple visualization, but it immediately highlights a key factor in the housing market.
Right. And then they go a step further and introduce correlation matrices, which help pinpoint the strongest connections between different factors.
Correlation matrices are essential for understanding which variables have the most significant influence on the outcome we're interested in.
Exactly. And in this case, they found that median income was the strongest predictor of housing prices.
Which makes sense.
Which makes total sense. The more people earn, the more they can spend on housing.
Yeah, it's a classic example of how ML can uncover intuitive relationships within complex data sets.
Yeah, and then the book doesn't stop at simple linear relationships. It goes into polynomial regression, showing how it can model those curvy, nonlinear trends that a straight line would miss entirely.
Yeah, polynomial regression is a great tool for capturing those more nuanced relationships.
Yeah.
Where the effect of one variable on another isn't constant.
And they illustrate this with a really interesting example. The relationship between life satisfaction and GDP. Turns out that beyond a certain point, more wealth doesn't necessarily equal more happiness.
Well, that's good to know.
Right.
Yeah.
So at a certain point,
Yeah, once you have your basic needs met, it's diminishing returns.
Yeah, and it really highlights the importance of choosing the right model complexity in ML.
Yeah, you can have a model that's too simple and it won't capture the true relationship.
Underfit.
Or you can have a model that's too complex.
Right.
And it'll start fitting to the noise in the data and not generalize well. Overfitting.
So it's all about finding that sweet spot.
Finding that sweet spot.
Right in the middle.
Yeah.
Okay, so let's shift gears a little bit and talk about kind of taming the data beast. The book emphasizes the importance of data quality.
Yeah.
And how it's just as crucial as the model that you choose.
Absolutely. The old saying, garbage in, garbage out.
Garbage in, garbage out.
Applies very much to ML.
Yeah. If you feed your model bad data, you're going to get bad results.
Right.
No matter how sophisticated the algorithm is.
Exactly. Spend the time to clean your data.
Yeah. And the book delves into some practical steps like data cleaning and handling those pesky missing values.
Which can be a real pain.
Yeah. And they even use the California housing data set again this time, showing how to deal with missing total bedrooms data.
Right. So you could...
Which is a very common problem, I'm sure.
Yeah, you could impute the missing values. You could remove the data points with missing values.
Yeah.
There are a lot of different ways to deal with missing data.
And then there's this cool concept of feature engineering.
Oh, yeah, feature engineering.
Where you create new attributes from existing data to improve the model's accuracy.
It's like giving your model a better set of lenses to see the world through.
Okay.
So instead of just looking at the total number of bedrooms, you could create a new feature called bedrooms per room or something like that.
Right.
That might be more informative for the model.
Yeah, I love that analogy. And the book even mentions Scikit-Learn's pipeline feature, which helps streamline the process of data cleaning and feature engineering.
Pipelines are great for automating and managing those pre-processing steps.
Yeah.
Ensuring consistency and reproducibility.
Okay, so now we've got our data cleaned, enhanced, ready to go.
Right.
Where does the book take us next?
Well, now we get to the fun part.
Okay.
We embark on a journey through some specific machine learning algorithms.
Okay.
Each with its strengths and weaknesses.
Right.
And the first stop on our journey is support vector machines, or SVMs.
SVMs, those sound kind of intense.
They might sound intimidating, but they're actually not yet bad.
Okay.
The book explains them in a very approachable way. Imagine you're trying to separate two groups of data points, say cats and dogs, based on their size and weight.
I can picture that.
So you've got all these points on a graph representing cats and dogs.
Yeah.
And an SVM aims to find the best line, or in higher dimensions, a hyperplane.
Okay.
That separates these two groups with the widest possible margin.
Okay.
Like a street between them.
I like that, a street.
Yeah, okay. The wider the street, the more confident we are in our classification.
So it's all about finding the best dividing line to maximize separation.
Exactly.
Okay.
And then the book moves on to decision trees, which operate more like a flowchart.
Okay.
Making decisions based on specific feature thresholds.
So like a game of 20 questions, but with data?
Precisely. The tree asks a series of questions about the data.
Okay.
Is the median income greater than X? Is the number of bedrooms greater than Y?
Right.
And based on the answers, it navigates down the branches of the tree until it reaches a final decision or prediction.
Okay, so I'm starting to see how these different algorithms offer unique ways of approaching a problem.
Yeah, they all have their own strengths and weaknesses.
So what's next on our algorithmic tour?
Next, we're introduced to ensemble learning.
Ensemble learning.
Which is all about combining the power of multiple models.
Okay.
To improve accuracy and robustness.
So instead of relying on one model, we're kind of tapping into the collective wisdom of a group.
That's a great way to put it. It's like getting a second opinion from a panel of experts.
Right.
Rather than just relying on one doctor.
Okay.
And the book's go-to example here is the random forest algorithm.
Random forest.
Which combines multiple decision trees.
Okay.
To create a more powerful and reliable predictor.
So it's like two heads are better than one.
Exactly.
Right.
Or in this case, many trees are better than one.
Many trees are better than one?
That's right.
All right, and now hold on tight because we're about to enter the realm of neural networks.
Neural networks. This is where things get really interesting.
This is where things get really futuristic.
Yeah, they're definitely one of the most exciting and rapidly developing areas of ML.
Yeah.
And they're inspired by the structure and function of the human brain.
Right.
Allowing them to learn complex patterns from data.
I know they're used in everything, from image recognition to...
Yeah, they're everywhere.
Natural language processing, but I have to admit the inner workings of neural networks have always seemed a bit mysterious to me.
Well, don't worry, the book starts with the basics.
Okay.
It explains the concept of artificial neurons, also known as perceptrons.
Perceptron.
Which act like tiny decision-making units, mimicking the behavior of biological neurons.
So they receive input signals, process them, and then fire off an output signal based on a certain threshold.
Exactly. Just like neurons in our brains.
Just like neurons in our brain.
And by connecting multiple layers of these artificial neurons, we can create multi-layer perceptrons, or MLPs.
MLPs.
These are powerful networks capable of learning incredibly complex patterns.
So it's like going from a single-story building to a towering skyscraper.
I like that analogy. More layers, more complexity, more power.
More layers, more complexity, more power.
That's right. And the book gives us a great example of MLPs in action.
Okay.
With the MNIST digit classification problem.
Yes, teaching a computer to recognize handwritten digits.
A classic example.
A classic.
Of how neural networks can tackle real-world challenges.
Absolutely. And to make things even easier, the book introduces us to Keras.
Keras.
A user-friendly library for building and training neural networks.
Yes, Keras is great. Think of it like having a high-level programming language.
Okay.
That hides a lot of the low-level complexities.
So it's like building with Lego blocks instead of starting from scratch.
Exactly.
With raw materials.
Keras makes it much easier to experiment with different neural network architectures.
Yeah.
And train them on your data.
That sounds much more approachable.
Much more approachable than trying to code everything from scratch.
Yeah, definitely. All right, so we've talked about building these neural networks.
Right. But how do we actually train them?
Yeah.
I know it involves feeding them tons of data, but...
Lots of data.
What's happening under the hood?
Well, training a neural network, or any machine learning model for that matter, is all about finding the optimal set of parameters that minimize a chosen cost function.
Okay.
So you can think of it like trying to find the lowest point in a valley.
Okay, we're trying to reach the bottom of the valley where our model's errors are minimized.
Exactly.
Yeah.
And one of the most common techniques for achieving this is called gradient descent.
Gradient descent, okay.
Imagine you're standing on a hillside and you want to get to the bottom of the valley.
Okay.
One strategy is to simply walk downhill in the direction of the steepest slope.
So the gradient is like the slope of the hill.
Yes.
And descent means we're walking downhill to reach the lowest point.
Exactly. And the learning rate is like the size of your steps.
Okay.
A large learning weight means you're taking big steps, which can be faster,
Right.
but also risk overshooting the lowest point. Okay.
A small learning rate means you're taking baby steps, which might be slower but more precise.
Got it. So we're gradually adjusting the model's parameters, taking steps in the direction that minimizes the errors.
That's a great way to put it.
But what if the valley has multiple dips and bumps? How do we make sure we're finding the
That's a great question.
absolute lowest point?
Yeah, and it's a common challenge in training neural networks.
Okay.
So you can get stuck in what's called the local minimum,
Right.
which is not the absolute lowest point.
Right.
So there are techniques to help us escape local minima
Okay.
and find the global minimum, the true bottom of the valley.
Got it.
One approach is stochastic gradient descent,
Okay.
where we randomly pick a single training instance at each step and compute the gradient based on that instance.
Okay.
This randomness can help us jump out of those pesky local minimums.
So like adding a bit of controlled chaos to the mix.
Exactly. Controlled chaos.
I'll avoid getting trapped.
Yeah.
Okay. Now another challenge that often arises, especially when training deep neural networks,
Right.
is the vanishing gradient problem.
Ah, yes, the vanishing gradient problem.
So what is that all about?
Remember how we talked about the gradient getting smaller
Yeah.
and smaller as we backpropagate errors?
Like the slope of the hill becoming almost flat as we get closer to the bottom.
Exactly. And when the gradient becomes too small, the weights in the earlier layers barely get updated.
Okay.
And training stalls.
So how do we overcome this vanishing gradient dilemma? Does the book offer any solutions?
It does. One common approach is to use activation functions that don't squash the gradients as much.
Okay.
A popular example is the rectified linear unit, or ReLU for short.
ReLU.
It's a simple function that outputs 0 for negative inputs
Okay.
and the input itself for positive inputs.
So it kind of acts like a switch, either letting the signal pass through unchanged
Exactly.
or blocking it completely.
And because it doesn't squash the gradients for positive inputs, it helps alleviate the vanishing gradient problem.
That's clever, but I'm guessing there are other tricks up our sleeve to combat these vanishing gradients.
There are. Another powerful technique is batch normalization.
Batch normalization.
This involves adding an extra layer that normalizes the inputs of each layer,
Okay.
ensuring that they have 0 mean and unit variance.
Okay.
This helps stabilize the gradients and speeds up training.
So it's like adding a quality control check at each step, making sure the signals are
Yeah, like a little bouncer at the door.
within a desired range and preventing them from getting too large or too small.
Exactly. Making sure everyone's behaving.
And speaking of challenges, another big one is the sheer amount of data required to train deep neural networks.
Oh yeah, they are data hungry.
It's like these models have an insatiable appetite
They can eat a lot of data.
for information.
For sure.
And sometimes getting enough labeled data can be a real bottleneck.
I feel it.
Is there a way to get around this data-hungry nature of deep learning?
Well, one solution is to leverage transfer learning.
Transfer learning.
The idea is to reuse parts of a pre-trained network.
Okay.
A network that's already been trained on a massive data set for a similar task.
So it's like saying, hey, this network already knows a lot about recognizing objects and images.
Right.
Let's borrow some of its knowledge and fine-tune it for our specific task.
Exactly. It's like taking advantage of someone else's hard work
Right.
and building upon their expertise.
That sounds incredibly efficient,
It is. It can save you a ton of time and resources.
especially when you don't have access to massive data sets yourself.
For sure.
Now let's talk about optimizing the training process itself.
Okay.
We've touched on gradient descent,
Right.
but are there other techniques that can speed things up?
Yeah, there are faster optimizers.
Okay.
One popular example is momentum optimization,
Momentum. Okay.
which considers the velocity of the gradient updates.
Okay.
It's like adding inertia to our descent,
Okay.
helping us move faster and smoother towards the minimum.
So instead of just taking steps based on the current slope, we're also considering the direction we were moving in previously.
Yeah, like a ball rolling down a hill.
Like a ball rolling down a hill.
It keeps going.
Okay.
Even if there's a little bump, it doesn't get stuck.
Right.
It keeps rolling.
This can help us accelerate through flat regions of the cost function.
Yes.
And avoid getting stuck in oscillations.
Exactly.
Okay.
It's a powerful way to speed up the learning process.
But speed isn't everything. We also need to make sure our model isn't becoming a know-it-all.
Right.
And failing to generalize to new data.
Ah, the dreaded overfitting problem.
The overfitting problem?
Where the model gets so good at fitting the training data
Yeah.
that it performs poorly on unseen data.
How do we prevent that?
Luckily, we have various regularization techniques to combat overfitting.
Regularization.
One popular technique is called dropout.
Dropout.
It might sound counterintuitive, but it involves randomly dropping out neurons during training, forcing the network to learn more robust and generalizable features.
So it's like introducing a bit of controlled chaos.
More controlled chaos.
To prevent the network from becoming too reliant on any single neuron or connection.
It's like making sure everyone's pulling their weight.
Okay.
Not just relying on one star player.
And another effective technique is early stopping.
Early stopping.
Where we stop training when the model's performance on a validation set starts to plateau or decrease.
Right. It's like saying, okay, you've learned enough. Don't overthink it.
Don't overthink it.
You're starting to memorize the training data.
Right.
We need you to generalize.
Early stopping makes sense. We want to find the sweet spot.
A sweet spot.
Where the model has learned enough to perform well on new data. But it hasn't started memorizing the training set.
Exactly.
Okay, and these are just a few of the many techniques used to prevent overfitting.
Right.
And ensure our models generalize well to new data.
Generalization is key.
Now, building and training these complex neural networks can be a daunting task.
It can be.
Are there any tools or frameworks that can help us manage this complexity?
Well, the book mentioned Keras, which is a great starting point.
Right.
But for more fine-grained control, there's also the lower-level TensorFlow API.
TensorFlow.
TensorFlow gives you more flexibility to define custom loss functions, metrics, and even create entirely new types of layers.
So it's like going from driving an automatic car to a manual transmission.
I like that analogy. More control, but also more responsibility.
More control, but also more responsibility.
Yes, you have to know what you're doing.
TensorFlow sounds powerful. Does the book dive into any specific TensorFlow features that are particularly useful?
It does. It covers TensorFlow functions, which are a way to optimize your code for performance.
Okay.
They essentially convert your Python function into computational graphs that TensorFlow can execute very efficiently.
So it's like taking our code and translating it into a language that TensorFlow understands perfectly.
Exactly, allowing it to run faster and smoother.
This is especially important when training large models on massive data sets where every bit...
when you're dealing with big data, every little bit of optimization helps.
Performance optimization counts.
For sure.
But handling massive data sets can be a challenge in itself. How does TensorFlow help us manage and process?
Well, that's where the TensorFlow Data API comes in.
Data API.
It provides a powerful set of tools for loading, transforming, and pre-processing data efficiently.
So it's like having a data Swiss Army knife.
I love it. A data Swiss Army knife.
Everything we need to prepare our data for the deep learning feast.
Exactly. It can handle large data sets that don't fit in memory.
Right.
And even pre-process data in parallel to speed up training.
The data API sounds like a lifesaver, especially when dealing with data sets that are too large to fit into memory.
It is. It can really make your life a lot easier.
Okay, so to further optimize data handling, the book introduces us to the T-freckled format.
T-freckled.
What's so special about that?
Well, T-freckled is TensorFlow's preferred format for storing and reading large data sets. It's a highly optimized binary format that makes data loading and processing much faster during training.
So it's like packing our data neatly into suitcases.
I like that. Packing our data.
For efficient transport and retrieval.
Makes sense.
Makes sense. Okay, but let's not forget that today's deep dive is all about...
deep learning.
Deep learning and computer vision.
Computer vision, that's right.
Where do convolutional neural networks fit into all of this?
CNNs. The superstars of image recognition.
CNNs. They're the superstars of image recognition and computer vision.
That's right. They're specifically designed to extract meaningful features from images.
Okay, but how do they actually work? I mean, images are just a bunch of pixels, right?
Yeah, but it's how those pixels are arranged.
How do they make sense of all that visual information?
That's the magic of CNNs. They have a special type of layer called a convolutional layer, which uses filters that slide across the image, detecting patterns and features at different scales.
So it's like breaking down the image into smaller pieces.
Yeah, like having a magnifying glass that scans the image.
And analyzing each piece for specific patterns.
Looking for specific shapes, edges, or textures.
Okay.
And by stacking multiple convolutional layers, we can learn increasingly complex and abstract features.
Right.
Allowing the network to recognize objects, scenes, and even faces with remarkable accuracy.
Now, I know there are tons of different CNN architectures out there. Does the book dive into any specific examples?
It does. It starts with the classic LINET 5 architecture,
Okay.
which was one of the pioneers of CNNs.
Right.
And then it walks us through some of the winners of the ImageNet Large-Scale Visual Recognition Challenge.
Okay, the big leagues of image recognition.
Or ILS-VRC for short.
What kind of architectures are we talking
Well,
about?
we get a glimpse into architectures like AlexNet, which really put CNNs on the map. GoogleNet, known for its inception modules.
Right.
That allowed for deeper networks.
Okay.
And ResNet, which introduced residual connections that further pushed the boundaries of CNN depth and performance.
This is all incredibly impressive. But I'm starting to realize that building and training these sophisticated CNNs
it can be a lot of work.
Can be a pretty daunting task. Are there any resources or tools that can help us get started without having to be